In this lecture, we will be looking at an example of using Newton's method for nonlinear optimization. So recall, this is a method we can use when we're trying to minimize a function, f of x, where x is a vector in Rn, and the objective function f is twice continuously differentiable. The example we will look at is given here. So we're minimizing f of x, where x is a vector in R2, and we have x1 minus 2 quantity to the fourth plus x1 minus 2 quantity squared times x2 squared plus x2 plus 1 quantity squared. And recall that this has a first order necessary condition of the gradient of f of x being equal to 0. And Newton's method, with a good choice of x naught, hopefully will converge to a solution of our first order necessary conditions. So this method picks up on saddle points, local minimizers, and local maximizers, but in this case, our f of x is convex, and so we're hoping that we can converge to a minimizer. We have here our theorem for the Newton method sequence. So we have our function f, twice continuously differentiable, and this gives us our iterative method. So recall here, this is the Hessian of f at the kth iteration, xk, times xk plus 1 minus xk equals the negative gradient of f at xk. And the idea here is in each iteration, we're solving for the next one. So we would be solving for xk plus 1. If we take this a step further and invert this Hessian, we can isolate xk plus 1 in this equation 3 given here. And we only have a solution if that is actually invertible, that Hessian is invertible. So the sequence doesn't necessarily converge for all functions, but if it does, often it will converge to a local minimizer of f. Like we said, it converges, if it does converge, it's converging where the necessary conditions are satisfied. So we take our example and we note from observation that the global solution is 2, negative 1. And we can see that by looking at each of these three terms. x1 minus 2 to the fourth, the smallest this can be is 0, which happens at x1 equals 2. x1 minus 2 squared, the smallest this can be is when x1 is equal to 2. Or if x2 is equal to 0, but we notice that x1 being 2 works. And then this last term, which only has x2 appearing, the smallest this can be is 0 when x2 is equal to minus 1. So we see that the solution 2 minus 1 will zero out each of these three terms in the sum. And so we confirm there that this is our solution. So let's see what happens if we start to iterate Newton's method. So first, we calculate our gradient. So our gradient here is the partial of f with respect to x1 for the first entry, and the partial of f with respect to x2 for the second entry. And when we do our partial derivatives, this is what we obtain. For our Hessian, recall that that is your matrix of second order derivatives. So the first term would be the second order partial of f with respect to x1 with respect to x1. Then we have the second order partial of f dx1 dx2. Down here, the second order partial of f dx2 dx1. And in the bottom right entry, the second order derivative of f with respect to x2 twice. And because f is continuously differentiable, these off-diagonal entries will be equal, giving us this symmetric Hessian. When we go through and calculate our second order partial derivatives, we obtain this matrix here. So let's start, and let's choose an initial guess of 1, 1. If we plug our initial guess of 1, 1 into the function, we will get 1 plus 1 plus 2 squared, or 6. So we see our objective function is starting out at a value of 6, and we're hoping to iterate to get down to a value close to 0. So let's set up for our Newton step. We need our gradient evaluated at this x naught, and we need our Hessian evaluated at this x naught. So let's take our previous calculation for the gradient and the Hessian, and let's plug in that x naught. So we'll plug in 1 for x1 and 1 for x2. So we see that here. We're plugging in 1 for x1 and 1 for x2. And when we evaluate this expression, we get minus 6, 6. We do the same for the Hessian. So we plug in 1 for x1 and 1 for x2. And when we do that, we end up with this matrix, 14 minus 4 minus 4, 4. Now we can use this for our Newton step. So recall, here is our Newton step. So the next iteration, which will be x1, we're going to plug in that x naught in these three instances to obtain this expression here. So our Hessian of f at x naught was this matrix, 14 minus 4 minus 4, 4. We're going to take the inverse of that. We plug in our gradient, minus 6, 6, and then we add x naught. The inverse of this Hessian is this matrix given here. When we calculate this, we end up with our next step, 1 minus 1/2. And notice, if we plug 1 minus 1/2 into our objective function, we get a value of 1.5. So we've reduced the value of the objective from 6 down to 1.5 in that first step. We can see that illustrated by looking at the graph. So here's the graph of our objective. We see the global solution down here in the x1, x2 plane. And here is our initial guess, x naught. This is our x1. So we can see we have moved down on the surface substantially through that first iteration. Let's continue and do a second iteration and see if we move further down the surface. So for our second iteration, we're using our x1, the 0.1, negative 1/2, and we're plugging that in to the gradient and to the Hessian of f. And note that what we have here is simply that gradient with 1 plugged in for x1 and minus 1/2 plugged in for x2. That gives us a gradient value of minus 4.5, 0 at this point x1. And we do the same for the Hessian, plugging in x1 equals 1 and x2 is minus 1/2. We get the matrix 12.5, 2, 2, 4. So this is the Hessian of f evaluated at the point x1. Bringing this information into our second iteration, where we will have x2 is the negative Hessian of f at x1 inverse, times the gradient of f at x1 plus x1, given here. We plug in. Our Hessian was 12.5224. Our gradient was minus 4.5, 0, and x1 was 1 negative 1/2. The inverse of this Hessian turns out to be this matrix here. And when we perform this multiplication and add 1 negative 1/2, we arrive at 1.39 negative 0.69. So note that this is getting closer to our global solution. And when we plug in this to our objective function, we get a value of 0.0409. So if we think about a progression, we started out at a value of 6, In the first iteration, we've reduced that value to 1.5, and now we've reduced the value to about 0.4. So in just 2 steps, we have gotten very close to that global objective value of 0. Graphically, we see that our x2 appears down here. So we can see our progression from x0 to x1 and x1 to x2. So it does look like we're honing in on that solution. If we continue in a third iteration, we get x3 as 1.746, negative 0.95. And you see this is getting closer to that 2, negative 1 global solution. And you see this x3 down here. So we took another step towards that global solution here. If we do one more iteration, the x4 is actually depicted here, but it's very hard to see that it's there because it's almost on top of the solution. And you see here we are very close. We're at 1.98 minus 1.05. And if you continue, we are in fact in this case converging to that solution. And you decide to stop based on criteria of how close you're actually getting. But this is a nice illustration and an example of how Newton's method progresses. And we can see our progression illustrated here.